Right now, at this very moment, somewhere on our planet, particles from the sun are dancing with Earth's magnetic field in a cosmic ballet that creates curtains of light across the polar skies. These ancient messengers, traveling millions of miles through the vacuum of space, are painting the darkness with colors that have stirred human hearts for thousands of years. Welcome to Sleep About Science. Tonight we're exploring the gentle mysteries of aurora lights, those shimmering ethereal displays that grace our planet's polar regions with their quiet magnificence. And if you drift off to sleep while listening, that's perfectly wonderful. In fact, there's something rather poetic about falling asleep to stories of these celestial lullabies. Before we begin, please make yourself comfortable. Pull that blanket a little closer, adjust your pillow just so. And remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. Wherever you are in the world right now, whether it's early morning in Tokyo, late evening in London, or the quiet hours of night in New York, you're part of our global community of curious minds who find peace in learning about the wonders that surround us. Now imagine for a moment that you're standing on a frozen lake in northern Norway, your breath forming small clouds in the crisp Arctic air. Above you, the sky begins to glow with an otherworldly light green curtains that seem to dance and flow like silk scarves in a gentle breeze. This is the Aurora Borealis, the northern lights, and what you're witnessing is the result of a story that began 93 million miles away on the surface of our sun. The sun, our nearest star, is not the steady, unchanging orb it appears to be from Earth. It's actually a churning, dynamic ball of plasma where temperatures reach millions of degrees. Deep within its core, nuclear fusion transforms hydrogen into helium, releasing enormous amounts of energy that eventually make their way to the sun's surface. But the sun doesn't just send us light and heat, it also sends us something called the solar wind. Picture the solar wind as an invisible river flowing outward from the sun in all directions. This isn't wind as we know it on Earth, made of air molecules. Instead, it's a stream of charged particles mined as protons and electrons racing through space at speeds of several hundred miles per second. It's been flowing for billions of years, and it will continue long after we're gone, an eternal current connecting our sun to the far reaches of our solar system. As these particles journey through space, most pass harmlessly by Earth, but our planet has a remarkable defense system, its magnetic field, generated deep within Earth's molten iron core. This invisible shield extends far out into space, creating a protective bubble called the magnetosphere. It's like Earth is wearing an enormous invisible cloak that deflects most of the solar wind around us, protecting our atmosphere and ultimately life itself. But here's where the magic begins. The solar wind particles don't simply bounce off our magnetic field like rain off an umbrella. Instead, some of them get caught and channeled along the magnetic field lines, like cars following invisible highways in the sky. These highways lead to Earth's polar regions, where the magnetic field lines converge and dive down into our atmosphere. When these charged particles finally encounter our atmosphere, roughly 60 to 200 miles above the surface, something wonderful happens. They collide with gas molecules, primarily oxygen and nitrogen, that make up our thin, high-altitude air. These collisions transfer energy to the gas molecules, exciting them, lifting their electrons to higher energy states. And when these excited atoms and molecules return to their normal state, they release that extra energy as light. It's a bit like when you were a child and someone showed you how to make sparks by striking flint against steel. The impact excites the metal, and it releases that energy as tiny flashes of light. The aurora works on a similar principle, but instead of metal sparks, we have glowing gases painting the entire sky. The colors you see in an aurora depend on which gas is glowing and at what altitude the collisions occur. Oxygen, when excited at higher altitudes around 200 miles up, produces that classic ethereal green that most people associate with the northern lights. It's the same green you might see if you could somehow bottle the essence of spring leaves or the glow of certain jellyfish in the deep ocean. At even higher altitudes, oxygen can produce a rare red glow, though this is much less common and requires particularly strong solar activity to be visible. Nitrogen contributes its own palette to this atmospheric art show. At lower altitudes, it creates blue and purple hues, while higher up it can produce a pink or magenta glow. Sometimes, all these colors blend together in the sky like watercolors spreading across wet paper, creating displays of such beauty that they seem almost too magnificent to be real. The shape and movement of auroras are equally mesmerizing. The classic aurora appears as curtains or drapery hanging in the sky, their lower edges often perfectly parallel to the ground. These curtains can stretch for hundreds of miles across the sky, yet be only a few miles thick. Imagine a wall of light so thin you could walk through it in just a few minutes, yet so vast it could span entire countries. But auroras don't just hang still like painted backdrops. They move and dance, pulsing with life. The curtains sway and ripple as the solar wind fluctuates, as if they're breathing with some cosmic rhythm. Sometimes they spiral into swirling coronas directly overhead, creating the impression that you're looking up through a tunnel of light into the very heart of the universe. Other times they break into discrete arcs or rays, like searchlights sweeping across the darkness. The movement isn't random mechanics. It follows the ever-changing patterns of Earth's magnetic field and the variable flow of the solar wind. During periods of high solar activity, when the sun releases particularly intense bursts of particles in what we call solar storms, the auroras become more active, more colorful, and can be seen much further from the poles than usual. During these geomagnetic storms, auroras have been spotted as far south as the Caribbean or Mediterranean mechanics. Imagine the surprise of someone in Greece or Mexico, looking up to see the northern lights dancing above their home. Indigenous peoples of the Arctic have watched these lights for thousands of years, and their cultures are rich with explanations and stories about what they represent. The Inuit of Alaska and northern Canada have various beliefs about the aurora nas and see them as the spirits of the dead playing football with a walrus skull, while others believe they're the souls of children who died in childbirth dancing in the sky. The Sami people of northern Scandinavia call them revontulet, which means firefox flames, imagining a magical Arctic fox running so fast across the snow that its tail sweeps up flakes that sparkle in the moonlight. In Finnish folklore, the aurora is caused by a magical firefox whose tail creates sparks as it runs across the snow. The word aurora itself comes from the Roman goddess of dawn, Aurora, though the scientific term aurora borealis was coined by the astronomer Galileo Galilei, combining aurora with boreas, the Greek name for the north wind. These cultural interpretations reveal something profound about human nature, our innate need to find meaning and story in the natural phenomena around us. Before we understood the science of charged particles and magnetic fields, our ancestors looked at these lights and saw dancing spirits, foxtails, and divine messages. In many ways, the scientific explanation is no less magical than these ancient stories. The idea that particles from our sun can travel across the vacuum of space to paint light across our sky is, when you really think about it, quite extraordinary. The aurora isn't unique to Earth either. Any planet with a magnetic field and an atmosphere can potentially have auroras, and we've observed them on Jupiter, Saturn, Uranus, and Neptune. Jupiter's auroras are particularly spectacular, hundreds of times more energetic than Earth's, creating displays that would dwarf anything we see here. They're powered not just by the solar wind but also by particles from Jupiter's volcanic moon Io, creating a complex interaction between the giant planet and its satellite that generates some of the most powerful auroras in our solar system. On Saturn, the auroras have a unique feature. They're influenced by the planet's rapid rotation, which creates a kind of magnetic slingshot effect that accelerates particles and creates particularly dynamic displays. These alien auroras remind us that the basic physics we see on Earth, the interaction between solar particles and magnetic fields, is universal, playing out in different ways throughout our solar system. But let's return to our own planet and consider the quiet majesty of experiencing an aurora firsthand. Many people describe seeing their first aurora as a transcendent moment, and it's easy to understand why. There's something humbling about standing under a sky filled with dancing light, knowing that what you're seeing is the result of processes that span from the heart of the sun to the upper reaches of our atmosphere. The best places to see auroras are within what scientists call the auroral oval minus roughly circular regions around the magnetic poles, where auroral activity is most common. In the north, this includes northern Alaska, northern Canada, Greenland, northern Scandinavia, and northern Siberia. In the south, the aurora australis, or southern lights, can be seen from Antarctica, southern Chile, southern New Zealand, and Tasmania. The timing matters too. Auroras are most visible during the equinoxes in March and September, when the orientation of Earth's magnetic field relative to the solar wind creates optimal conditions for these celestial displays. They're also more frequent during the peak of the 11-year solar cycle, when the sun is most active and sending more charged particles our way. If you ever find yourself in a place where auroras are visible, there are some practical considerations for the best viewing experience. You'll want to be away from city lights, as light pollution can wash out all but the brightest auroral displays. The ideal viewing conditions include clear, dark skies and a new moon or one that sets early in the evening, Dress warmly. Midas auroral watching often requires patience and stillness in cold climates, and bring a comfortable chair or blanket, because you might find yourself gazing upward for hours. Many people are surprised to learn that auroras make sound, though this was debated by scientists for many years. Indigenous observers had long reported hearing the lights, describing sounds like crackling, hissing, or swooshing that seemed to accompany particularly bright displays. For decades, scientists were skeptical, because the auroras occur so high in the atmosphere that sound waves shouldn't be able to travel down to ground level. Recent research has confirmed that auroras can indeed produce sound, though the mechanism is different than what scientists initially expected. The sounds aren't coming from the high-altitude aurora itself, but rather from electrical activity much closer to the ground that's triggered by the same magnetic disturbances that create the lights. It's as if the aurora is conducting an invisible orchestra of electrical discharges in the atmosphere much closer to Earth's surface. These sounds are typically very quiet and require very still conditions to hear. They're described as subtle crackling or rustling, almost like the sound of paper being crumpled very gently, or like static electricity discharging. The fact that these sounds exist at all adds another layer of wonder to the auroral experience. Not only are you seeing this cosmic light show, but in the right conditions you're hearing it too. The aurora also has practical implications beyond its beauty. The same geomagnetic storms that create spectacular auroral displays can interfere with our technological systems. Radio communications can be disrupted, GPS signals can become unreliable, and in extreme cases, power grids can be affected. The famous Carrington event of 1859 was a massive geomagnetic storm that caused auroras to be visible as far south as the Caribbean, but also induced electrical currents so strong that telegraph systems worldwide failed, with some operators receiving electric shocks and telegraph paper catching fire. In our modern, electronically connected world, we're more vulnerable to such events than the Victorians with their telegraph systems. Satellites can be damaged by intense radiation during severe geomagnetic storms, affecting everything from weather forecasting to internet communications. Airlines sometimes reroute polar flights during severe storms to avoid radio blackouts and reduce radiation exposure for passengers and crew. It's a reminder that while auroras are beautiful, they're also symptoms of powerful forces at work in our solar system. Scientists study auroras not just for their beauty, but because they provide a visible window into the invisible interactions between the Sun and Earth. Auroras are natural laboratories for understanding plasma physics, the behavior of charged particles in magnetic fields, and the complex dynamics of our planet's magnetosphere. Research stations in places like Alaska and northern Canada are equipped with sophisticated instruments that measure everything from the energy of incoming particles to the exact wavelengths of light being produced by different atmospheric gases. This research has practical applications beyond simply understanding auroras. The same processes that create auroras are at work in many other areas of physics and astronomy. Understanding how charged particles interact with magnetic fields helps us design better fusion reactors, comprehend the behavior of distant stars, and predict space weather that could affect astronauts and satellites. The aurora borealis and aurora australis are also connected in ways that might surprise you. They often occur simultaneously, as if they're mirror images of each other at opposite ends of the planet. When the solar wind hits Earth's magnetic field, it doesn't just affect one hemisphere. The disturbance travels along magnetic field lines that connect the north and south polar regions. So when someone in Alaska is watching green curtains dance across the northern sky, there's a good chance that someone in Antarctica is seeing a similar display in the south. This connection extends to the detailed patterns as well. High-speed cameras and satellite observations have shown that the northern and southern auroras often move in synchronized patterns, pulsing and swirling together like two parts of the same cosmic symphony. It's a beautiful reminder of how interconnected our planet's systems are, and how phenomena that seem local are often part of much larger global processes. As we've explored the science behind auroras, it's worth taking a moment to appreciate the sense of scale involved. The journey of a solar particle from the sun to your eye during an aurora is truly epic. That particle began its journey in the nuclear furnace of the sun's core, where it may have spent thousands of years working its way to the surface through the dense solar interior. Once it escaped into space as part of the solar wind, it traveled for several days across 93 million miles of vacuum. Then it was caught by Earth's magnetic field, channeled along invisible field lines, and finally collided with an oxygen or nitrogen molecule in our upper atmosphere, causing it to glow with just the right color and intensity for you to see. Each photon of light that reaches your eye from an aurora has been on this incredible journey, carrying energy that originated in stellar nuclear fusion and has been transformed and transferred through multiple stages to become the gentle glow you see dancing across the sky. When you watch an aurora, you're seeing the end result of processes that span from the quantum scale of atomic interactions to the astronomical scale of our solar system. There's something profoundly peaceful about this perspective. The aurora connects us to the cosmos in a very direct way. Minus the light you see is created by our sun, channeled by our planet's magnetic field, and produced by the very atmosphere we breathe. It's a reminder that we're not separate from the universe around us, but part of an interconnected system of matter and energy that spans from the smallest particles to the largest structures in space. For those who have never seen an aurora in person, it might be hard to understand why people travel to remote, cold places specifically to witness these displays. But there's something about seeing an aurora that photographs and videos can't quite capture. It's partly the scale. Minus auroras can stretch across the entire visible sky, creating an immersive experience that surrounds you with light. It's partly the movement, the way the curtains sway and pulse with their own rhythm, sometimes slow and stately, sometimes fast and energetic. But perhaps most importantly, it's the context. When you see an aurora, you're usually in a very quiet, often remote place. You're away from the noise and lights of cities, standing under a vast dark sky filled with stars. The aurora appears against this backdrop of cosmic immensity, creating a moment of connection between the immediate and the infinite. Many people describe the experience as spiritual, not in any religious sense necessarily, but in the way it puts human life into perspective and creates a sense of wonder about our place in the universe. The aurora also changes throughout the night and across seasons in ways that make each viewing unique. Early in the evening, you might see just a faint green glow on the horizon, so subtle you might wonder if it's just clouds. As the night progresses and conditions change, this glow might brighten and begin to form distinct shapes. First perhaps a simple arc across the sky, then curtains, then complex spirals and coronas. The intensity can vary dramatically within minutes. A quiet, barely visible aurora can suddenly burst into brilliant activity, filling the sky with rapidly moving curtains of light before fading back to a gentle glow. These bursts, called auroral substorms, are caused by sudden releases of energy stored in Earth's magnetic field, like a rubber band that's been stretched too far and suddenly snaps back. During the peak of a display, the aurora can be bright enough to cast shadows on the snow and illuminate the landscape with an ethereal green light. Trees, mountains, and frozen lakes take on an otherworldly appearance under this natural illumination, creating scenes that look almost like they belong on an alien planet. The silence of these moments is often profound, mindless, just you, the landscape, and the dancing lights above. As winter progresses toward spring in the polar regions, the auroral activity often increases, reaching a peak around the time of the spring equinox in March. This is due to the way Earth's magnetic field is oriented relative to the solar wind at different times of year. During equinoxes, the geometry is optimal for solar particles to penetrate into our magnetosphere, creating some of the most spectacular displays of the year. But even during quieter periods, there's often some auroral activity visible to those who know where and when to look. Dedicated aurora watchers develop an almost intuitive sense for when conditions might be favorable. They watch space weather forecasts, monitor solar activity, and track the movements of high-speed solar wind streams that might interact with Earth's magnetosphere in just the right way to create a display. The patience required for aurora watching has its own rewards. Spending hours under a dark sky, even when the aurora isn't active, connects you to the rhythms of the natural world in a way that our modern indoor lifestyles rarely allow. You become aware of how the stars wheel overhead, how the temperature drops as the night progresses, how the landscape takes on different moods under starlight. When the aurora does appear, it feels like a gift, a reward for your patience and dedication. Photographers who specialize in capturing auroras develop an intimate relationship with these lights. They learn to predict not just when auroras might occur, but how they might behave. They understand that the camera can sometimes reveal colors and structures that the naked eye can't see, particularly the red colors that require darker skies and more sensitive equipment to observe. But they also know that no photograph can fully capture the experience of standing under an active aurora display. The aurora photography community has grown significantly with the advent of digital cameras and social media. Images of spectacular auroral displays can now be shared instantly with people around the world, bringing the beauty of these lights to those who may never have the opportunity to see them in person. While this sharing is wonderful, it also creates sometimes unrealistic expectations about what auroras look like to the naked eye. Many aurora photographs are taken with long exposures or enhanced processing that brings out colors and details that might not be immediately visible to someone standing in the same spot. The human eye, while remarkably adaptable, doesn't see in quite the same way a camera sensor does. This doesn't make the photographs less valid or beautiful, but it's worth understanding that the experience of seeing an aurora in person might be more subtle and nuanced than some photographs suggest. That said, the human eye has its own advantages for aurora watching. We perceive movement and change much better than any single photograph can capture. We see the aurora as a dynamic, living thing, constantly shifting and evolving. Our eyes also adapt to darkness much better than most camera sensors, allowing us to see faint auroral displays that might not register on camera at all. The seasonal rhythm of aurora watching in the far north creates its own culture and community. During the long polar winter, when nights can last for months, aurora watchers develop patterns and rituals. They know the best viewpoints, the clearest nights, the subtle signs that herald a good display. Hotels and tour operators in places like northern Alaska, northern Canada, and northern Scandinavia cater specifically to aurora tourism, offering heated viewing cabins, wake-up calls for unexpected displays, and guides who know the local conditions intimately. But you don't need to travel to the Arctic to participate in aurora science. Citizen scientists around the world contribute to aurora research by reporting sightings, taking photographs, and even monitoring radio signals that are affected by auroral activity. Apps and websites allow people to receive alerts when auroras might be visible at their location and to share their observations with the global aurora watching community. For those living at lower latitudes, the occasional aurora visible during major geomagnetic storms creates a special sense of excitement. When auroras appear in places like Scotland, northern United States, or southern New Zealand, word spreads quickly through social media and astronomy clubs. People who have never seen an aurora before venture out into their backyards or drive to darker locations, hoping to catch a glimpse of lights they've only seen in photographs from far northern or southern locations. These lower latitude auroras are often different from their polar cousins. They may appear as a red glow on the horizon rather than the classic green curtains, or as faint pillars of light that come and go quickly. They require darker skies to be visible, and are often much more subtle than the displays seen in the auroral zones. But for many people, seeing any aurora, however faint, becomes a memorable experience that connects them to the larger cosmic processes happening around our planet. The study of auroras has also led to advances in our understanding of other astronomical phenomena. The same physics that creates auroras on Earth helps us understand the behavior of stellar coronas, the interaction between stellar winds and planetary magnetospheres around other stars, and the complex plasma physics that govern everything from the Sun's magnetic field to the formation of galaxies. Some of the most exciting recent discoveries in aurora science have come from space-based observations. Satellites positioned in various parts of Earth's magnetosphere can measure the aurora from multiple angles simultaneously, revealing three-dimensional structures and behaviors that are impossible to see from the ground. These observations have shown that auroras are far more complex and variable than ground-based viewing suggests, with intricate structures and rapid changes occurring on scales from meters to thousands of kilometers. One particularly fascinating discovery is that auroras can create their own weather systems in the upper atmosphere. The energy deposited by auroral particles can heat the atmosphere and create winds and circulation patterns that are completely different from the weather we experience at ground level. These high-altitude aurora-induced weather systems can affect satellite orbits, radio propagation, and even the chemistry of the upper atmosphere. The aurora also plays a role in the loss of atmospheric gases to space. While Earth's magnetic field protects us from most of the solar wind, the same processes that create beautiful auroral displays also allow some of our atmosphere to escape. Particles energized by auroral processes can reach escape velocity and be lost to space permanently. This happens very slowly, but over geological timescales, it's one of the processes that affects the long-term evolution of planetary atmospheres. Mars provides a sobering example of what can happen to a planet that loses its global magnetic field. Early in its history, Mars had a thicker atmosphere and may have had auroras similar to Earth's, but when Mars lost its global magnetic field, it also lost much of its ability to protect its atmosphere from the solar wind. Over billions of years, much of Mars's atmosphere was stripped away, leaving the thin, cold atmosphere we see today. While Mars still has localized magnetic fields that can create small-scale auroral displays, they're nothing like the global phenomena we see on Earth. This connection between auroras and atmospheric evolution makes the study of our own auroral displays more than just an academic curiosity. Understanding how our magnetosphere and aurora system work helps us appreciate the delicate balance that makes Earth habitable and gives us insights into how other planets, both in our solar system and orbiting distant stars, might maintain or lose their atmospheres over time. As we've journeyed through the science and beauty of auroral displays, it's worth reflecting on what these lights represent in the larger story of our relationship with the cosmos. For most of human history, the aurora was mysterious and unexplainable, something that inspired awe and sometimes fear. Our ancestors created elaborate mythologies to explain these lights, weaving them into their understanding of life, death, and the supernatural. The scientific explanation we have today doesn't diminish the wonder of auroras pluribus. If anything, it enhances it. Knowing that these lights are created by particles from our sun, guided by our planet's magnetic field, and painted across our sky by the very air we breathe, makes them more remarkable, not less. The aurora is a visible reminder of the invisible forces that shape our world and connect us to the larger universe. In our modern world, where so much of our experience is mediated by screens and artificial environments, the aurora offers something increasingly rare: a direct, unmediated encounter with natural phenomena on a cosmic scale. When you stand under an active aurora display, you're seeing something that no human technology created or controls. You're witnessing the real-time interaction between our sun and our planet, played out across the canvas of our sky. This direct connection to cosmic processes has a way of putting daily concerns into perspective. The aurora operates on timescales that span from the split-second collisions of individual particles to the multi-billion-year evolution of our solar system. Standing under these lights connects you to both the immediate moment and the deep time of cosmic evolution. The aurora also reminds us of our planet's unique position and characteristics. Not all planets have auroras, and even those that do have displays that are different from ours. Earth's aurora is the result of a specific combination of factors: our distance from the sun, the strength and configuration of our magnetic field, the composition of our atmosphere, that makes our particular version of this cosmic light show possible. As we learn more about planets orbiting other stars, we're beginning to understand that Earth-like auroras might be quite rare in the universe. While the basic physics of charged particles interacting with magnetic fields is universal, the specific conditions that create the gentle, beautiful displays we see from Earth may be uncommon. This makes our auroras not just beautiful but precious reminder of how special our planet's situation really is. For those planning to see an aurora for the first time, it's worth managing expectations while also preparing for wonder. The aurora is highly variable. You see anything from a faint glow on the horizon to brilliant curtains filling the entire sky. Weather, solar activity, and even the phase of the moon all affect what you'll see, but patience and persistence are often rewarded, and even a subtle aurora can be a profound experience when it's your first. The key is to approach aurora watching with a sense of openness and acceptance. Like many natural phenomena, auroras operate on their own schedule and follow their own patterns. You can increase your chances of seeing them by choosing the right location and time, but ultimately, the aurora will do what it will do. This unpredictability is part of what makes seeing an active aurora so special. It feels like a gift rather than something you can simply demand. The best aurora experiences often happen when you least expect them. Many aurora watchers have stories of spectacular displays that appeared during routine trips or casual glances out the window. There's something magical about these unexpected encounters, as if the aurora is rewarding those who pay attention to the sky rather than those who actively seek it out. The aurora also has a way of creating community among those who witness it. Strangers will stop their cars to watch together, sharing the experience and excitement of seeing something extraordinary. Online communities of aurora watchers share information, photographs, and forecasts, creating global networks of people united by their appreciation for these cosmic displays. This sense of community extends to the scientific research as well. Aurora science is truly international, with researchers from many countries collaborating to understand these phenomena. Data from ground-based observatories in Alaska might be combined with satellite measurements from European missions and theoretical models developed by scientists in Japan or Russia. The aurora itself doesn't recognize national boundaries. It's a planetary phenomenon that brings out the collaborative spirit in human scientific endeavors. As our technology advances, new ways of studying and experiencing auroras continue to emerge. Virtual reality systems can now simulate aurora displays, allowing people who may never travel to polar regions to experience something approaching the immersive nature of standing under these lights. While nothing can fully replace the real experience, these technological approaches can help more people understand and appreciate what they're seeing when they do encounter auroras. Real-time aurora forecasting has also improved dramatically, thanks to better understanding of solar wind patterns and more sophisticated space weather monitoring. Spacecraft positioned between Earth and the Sun can provide hours of advance warning when conditions favorable for auroral displays are approaching. This allows both scientists and aurora watchers to prepare for potentially spectacular events. Climate change is also affecting aurora research and viewing. As the Arctic warms, weather patterns in auroral viewing regions are changing, affecting cloud cover and visibility. Some traditional aurora viewing locations are becoming less reliable due to changing precipitation patterns, while others might become more accessible as temperatures moderate. These changes add another layer of complexity to aurora tourism and scientific observation programs. The relationship between human activity and the aurora is becoming more complex in other ways as well. As we launch more satellites and create more electromagnetic interference, the environment in which auroras occur is becoming more crowded and noisy. Radio emissions from human technology can interfere with the natural radio phenomena associated with auroras, potentially affecting both scientific study and the natural experience of these displays. Light pollution continues to be a major challenge for aurora viewing. As more of the world's population lives in cities and suburban areas with significant artificial lighting, the number of places where faint auroras can be seen continues to shrink. This makes the remaining dark sky locations even more precious and important to protect. Despite these challenges, interest in auroras continues to grow. Social media has allowed spectacular aurora photographs and videos to reach audiences that previous generations could never have imagined. This increased awareness is creating new appreciation for the science behind these displays and driving more people to seek out aurora experiences for themselves. The aurora also continues to surprise researchers with new phenomena and unexpected behaviors. Recent discoveries include new types of auroral displays with names like Steve, strong thermal emission velocity enhancement, and dunes, which were first identified by citizen scientists and amateur photographers before being studied by professional researchers. These discoveries remind us that there's still much to learn about these familiar yet mysterious lights. As we look to the future, aurora research is likely to benefit from even more sophisticated satellite missions, better theoretical models of magnetospheric processes, and continued collaboration between professional scientists and amateur observers. New space missions are planned to study the aurora from multiple vantage points simultaneously, providing three-dimensional views of how these displays develop and evolve. The aurora may also play a role in future human activities in space. As we establish permanent bases on the Moon or plan missions to Mars, understanding space weather and its effects becomes increasingly important. The same solar storms that create beautiful auroras on Earth can be dangerous to astronauts and spacecraft, making aurora research part of the essential knowledge needed for safe space exploration. But perhaps the most important aspect of the aurora is not scientific or practical, but experiential and emotional. In a world that often feels disconnected from nature, the aurora provides a direct, visceral reminder of our planet's place in the cosmos. It connects us to the sun that powers all life on Earth, to the magnetic field that protects us, and to the thin atmosphere that surrounds our world. When you stand under an aurora display, you're participating in a tradition that stretches back to the first humans who looked up at these lights with wonder. You're seeing the same basic phenomenon that inspired countless generations of storytellers, artists, and scientists. Yet your experience is also unique because no two aurora displays are exactly alike, and your particular vantage point in time and space will never be repeated. The aurora reminds us that the universe is not a cold, empty place, but a dynamic, interconnected system of matter and energy in constant motion and interaction. The particles that create the lights you see have journeyed from the heart of the sun, through the emptiness of space, and into our atmosphere, where they paint the sky with colors that speak to something deep in human nature. As we continue to explore and understand our universe, the aurora serves as a bridge between the scientific and the sublime. It's a phenomenon that can be measured, predicted, and explained, yet it retains the power to move us emotionally and spiritually. It represents the best of human curiosity, our desire to understand the natural world combined with our capacity to find beauty and meaning in that understanding. Whether you see your first aurora as a faint green glow on a distant horizon, or as brilliant curtains filling the entire sky, you become part of this continuing human relationship with one of nature's most beautiful displays. You join the countless generations of people who have looked up at these lights and felt connected to something larger than themselves. The aurora teaches us patience, as it operates on its own schedule and cannot be hurried. It teaches us humility, as it reminds us of the vast forces at work in our solar system. and it teaches us wonder, as it reveals beauty in the intersection of science and nature that continues to inspire awe, no matter how well we understand the mechanisms behind it. In the end, the aurora is both a scientific phenomenon and a work of art, both a consequence of cosmic physics and a source of human joy. It's a reminder that we live on a planet that is active and dynamic, protected and blessed, connected to the stars, and yet unique in its particular combination of circumstances that makes these displays possible. As you drift off to sleep tonight, wherever you are in the world, you might imagine those solar particles continuing their ancient journey from the sun to Earth, painting colors across polar skies for anyone patient and fortunate enough to witness them. And perhaps, in your dreams, you'll find yourself standing under a canopy of dancing lights, feeling the connection between the cosmic and the intimate that the aurora represents so beautifully. The aurora will continue to dance across our skies long after we're gone, a testament to the enduring processes that shape our planet and our solar system. But for now, for this moment, we're here to witness and appreciate these lights, to study them and wonder at them, and to find in their gentle glow a source of peace and connection to the vast, beautiful universe that surrounds us. Sweet dreams, and may your nights be filled with the gentle light of understanding and wonder. The story of the aurora is also intimately connected to the story of our planet's magnetic field, one of the most remarkable and least understood aspects of Earth's character. Deep beneath our feet, roughly 1,800 miles down, lies Earth's outer core, mighty churning ocean of liquid iron and nickel heated to temperatures that rival the surface of the sun. This molten metal moves in complex patterns driven by the rotation of our planet and the cooling of the inner core, creating electrical currents that generate the magnetic field that makes auroras possible. This geodynamo, as scientists call it, has been operating for billions of years, though it hasn't always been stable. The geological record shows us that Earth's magnetic field has reversed many times throughout history, the north magnetic pole becoming the south magnetic pole, and vice versa. These reversals happen irregularly, sometimes separated by hundreds of thousands of years, other times occurring much more frequently. During these magnetic reversals, the strength of Earth's magnetic field can drop dramatically, sometimes to just 10% of its normal intensity. If such a reversal were to occur today, it would significantly affect the aurora patterns we're familiar with. Auroras might appear at much lower latitudes, or they might become much more chaotic and unpredictable as the weakened magnetic field struggles to channel solar particles along organized pathways. The last major magnetic reversal occurred about 780,000 years ago, well before modern humans evolved. But we can study these ancient reversals by examining the magnetic orientation of rocks and sediments laid down during different geological periods. Iron-bearing minerals in cooling lava, for instance, align themselves with the prevailing magnetic field, creating a permanent record of the field's direction at the time the rock solidified. These studies reveal that during some periods in Earth's history, the magnetic field was much stronger than it is today, while during others it was significantly weaker. A stronger magnetic field would have created more intense auroral activity, potentially making these displays visible much further from the poles than they are now. Early humans living during such periods might have regularly witnessed auroras from locations where they're never seen today. The strength and configuration of Earth's magnetic field also affects which solar particles can penetrate into our atmosphere. During periods of weaker magnetic protection, more high-energy particles would reach the upper atmosphere, potentially creating more red auroras major, the type that requires the most energetic collisions to produce. Ancient skies might have been painted with colors and intensities we can only imagine today. But the magnetic field does more than just create pretty lights. It's one of the key factors that has allowed complex life to develop on Earth. Without this invisible shield, the solar wind would gradually strip away our atmosphere, as appears to have happened to Mars. The magnetic field also protects us from much of the harmful cosmic radiation that constantly bathes our solar system, radiation that would be lethal to most life forms if it reached Earth's surface in full intensity. When we watch an aurora, we're seeing visible evidence of this protection in action. The dancing lights are proof that our planet's magnetic shield is working, channeling dangerous charged particles away from our vulnerable atmosphere and biosphere. In this sense, the aurora is not just beautiful, it's a sign of our planet's health and vitality. The solar particles that create auroras are part of a much larger and more complex system of space weather that affects our entire solar system. The sun's magnetic field, unlike Earth's relatively stable dipolar field, is incredibly dynamic and chaotic. Solar magnetic field lines can become tangled and twisted as different parts of the sun rotate at different speeds, building up enormous amounts of stored energy. When these twisted magnetic field lines suddenly snap and reconnect, they release tremendous amounts of energy in events called solar flares. These flares can accelerate charged particles to incredible speeds, creating streams of high-energy protons and electrons that race outward from the sun at velocities that can exceed normal solar wind speeds by orders of magnitude. When these enhanced particle streams reach Earth, they can create some of the most spectacular auroral displays ever witnessed. The Great Aurora of 1859, known as the Carrington Event, was caused by just such a solar storm. Auroras were visible as far south as the Caribbean and Hawaii, appearing with colors and intensities that amazed observers worldwide. Telegraph systems failed globally, with some operators receiving electric shocks and telegraph wires sparking fires. But the Carrington Event, dramatic as it was, pales in comparison to some of the solar storms that have occurred throughout Earth's history. Ice cores from Greenland and Antarctica contain chemical signatures of much more powerful solar events, storms that would have created auroral displays of unimaginable intensity and beauty. During these ancient superstorms, the entire night sky might have glowed with auroral light, creating global displays that lasted for days or weeks. If such a storm were to occur today, it would likely cause widespread disruption to our electronic infrastructure. Power grids could fail across entire continents, satellites could be permanently damaged, and radio communications could be disrupted for extended periods. Yet from an aurora watcher's perspective, it would also create the most spectacular light show in recorded human history. The relationship between solar activity and auroral displays follows an 11-year cycle known as the solar cycle. During solar minimum, when the sun is relatively quiet, auroral activity is generally confined to the polar regions and tends to be less intense and colorful. During solar maximum, when the sun is most active, auroras become more frequent, more intense, and can be seen much further from the poles. But even within this 11-year cycle, solar activity can be highly unpredictable. The sun can be quiet for months and then suddenly produce a series of powerful flares and coronal mass ejections. Conversely, during periods when solar activity is expected to be high, the sun can sometimes enter surprisingly quiet phases that last for weeks or months. This unpredictability is part of what makes aurora watching so exciting and challenging. Unlike many astronomical phenomena that can be predicted years in advance, auroras depend on solar activity that can change dramatically within hours or days. Aurora forecasters work with sophisticated computer models and real-time data from spacecraft monitoring the sun, but even the best forecasts can only provide probabilities and rough timelines rather than precise predictions. The spacecraft that monitor space weather and provide aurora forecasts are marvels of engineering in their own right. The Solar and Heliospheric Observatory, known as SOHO, has been watching the sun continuously for more than 25 years from a position about 1 million miles from Earth. From this vantage point, SOHO can observe solar flares and coronal mass ejections as they happen, providing several hours of advance warning before the effects reach Earth. The Advanced Composition Explorer, or ACE, sits at the same gravitational balance point as SOHO, directly between Earth and the Sun. ACE measures the solar wind in real time, detecting changes in particle density, speed, and magnetic field orientation that herald the arrival of solar storms. When ACE detects the signature of an approaching coronal mass ejection, aurora watchers around the world receive alerts that spectacular displays may be imminent. More recently, the Parker Solar Probe has begun the most ambitious solar observation mission ever attempted, actually flying through the sun's outer atmosphere to study solar wind acceleration and magnetic field dynamics at their source. Data from Parker Solar Probe is revolutionizing our understanding of how solar storms develop and propagate, potentially leading to much more accurate aurora forecasts in the coming years. But spacecraft observations are only part of the story. Ground-based observatories around the world contribute crucial data to our understanding of how solar storms affect Earth's magnetosphere and create auroral displays. The SuperDARN network of radars can track the movement of charged particles through the upper atmosphere, while magnetometer stations monitor changes in Earth's magnetic field that accompany auroral activity. All sky cameras at dozens of locations throughout the auroral zones photograph the sky continuously throughout the night, creating time-lapse sequences that reveal the development and evolution of auroral displays. These cameras often capture auroral activity that no human observer witnesses, providing a continuous record of how auroras behave under different conditions. The data from all these sources is combined in sophisticated computer models that attempt to predict when and where auroras will appear. These models simulate the interaction between the solar wind and Earth's magnetosphere, tracking how disturbances propagate through the system and where they're most likely to produce visible auroral activity. While these models have become increasingly accurate over the past decade, aurora forecasting remains as much art as science. Experienced forecasters learn to recognize subtle patterns in the data that might indicate unusual or particularly active conditions. They develop intuitive understanding of how different types of solar storms affect auroral activity, knowledge that can't easily be captured in computer algorithms. This blend of high-tech monitoring and experienced interpretation reflects the complex dynamic nature of the aurora itself. While we understand the basic physics of how charged particles create auroral light, the details of when, where, and how intense that light will be depend on countless variables interacting in ways that are still not fully understood. The aurora research community has also embraced citizen science in remarkable ways. Amateur photographers and aurora enthusiasts often capture images of unusual auroral phenomena before professional researchers notice them. The discovery of Steve, the unusual purple and green auroral display that has captured widespread attention in recent years, began with citizen scientists sharing photographs of something that didn't match known auroral categories. Steve appears as a narrow ribbon of purple light accompanied by green picket fence structures, quite different from the flowing curtains of typical auroras. Professional researchers initially dismissed early reports as misidentified normal auroras, but persistent documentation by amateur observers eventually led to dedicated scientific investigation that revealed Steve to be a previously unknown phenomenon with its own unique physics. The discovery of Steve illustrates how much we still don't know about auroral processes, even after more than a century of scientific study. It also demonstrates the value of having thousands of people around the world regularly observing and photographing the aurora. Professional researchers, no matter how dedicated, simply can't monitor every aurora that occurs, making citizen contributions essential for advancing our understanding of these complex phenomena. Social media has transformed how aurora information spreads and how the aurora watching community connects. Real-time sharing of aurora photographs and observations allows people to track auroral activity as it develops across different time zones. When a major auroral storm begins in Alaska, observers in northern Canada and Scandinavia can prepare for displays that might reach them hours later as Earth rotates into the optimal viewing geometry. This global communication network has also helped democratize aurora watching to some degree. People who live in regions where auroras are rarely visible can now follow aurora activity in real time, vicariously experiencing displays through the photographs and reports of others. While nothing replaces seeing an aurora in person, this virtual participation has created a global community of aurora enthusiasts who share knowledge, forecasts, and excitement about these cosmic light shows. The economic impact of aurora tourism has grown substantially in recent years, bringing both opportunities and challenges to remote northern communities. Fairbanks, Alaska, Yellowknife, Canada, Tromsø, Norway, and Reykjavik, Iceland have all developed substantial tourism industries based largely on aurora viewing, with specialized hotels, tour operators, and guide services catering to visitors from around the world. This aurora tourism boom has brought economic benefits to regions that have historically struggled with limited economic opportunities. Hotels report occupancy rates that spike dramatically during periods of high auroral activity, and local guides who understand aurora science and optimal viewing conditions have found new sources of income. Some communities have built entire winter tourism seasons around aurora viewing, offering everything from heated viewing pods to aurora-focused photography workshops. But aurora tourism also presents challenges. Many of the best aurora viewing locations are in environmentally sensitive areas where increased human activity can have negative impacts. The bright lights required for tourist facilities can create light pollution that interferes with aurora viewing. And the unpredictable nature of auroral activity means that many visitors travel great distances only to encounter cloudy skies or low solar activity that prevents them from seeing the displays they hope to witness. Responsible aurora tourism requires balancing economic opportunity with environmental protection and realistic expectations. The best aurora tour operators educate their clients about the science behind auroral displays, help them understand the factors that affect visibility, and provide alternative activities for nights when aurora viewing isn't possible. They also work to minimize light pollution and environmental impact, recognizing that preserving the pristine conditions that make aurora viewing possible is essential for the long-term sustainability of their business. The aurora has also inspired countless artists, writers, and musicians throughout history. Painters have struggled to capture the dynamic movement and ethereal colors of auroral displays, while writers have used aurora imagery to evoke everything from romance to cosmic terror. The challenge of representing something so inherently dynamic and three-dimensional in static, two-dimensional media has pushed artists to develop new techniques and approaches. Classical composers have written pieces inspired by the aurora, attempting to translate the flowing movement and changing intensities of auroral displays into musical form. The aurora's tendency to build slowly, reach moments of intense activity, and then fade back to subtle glows provides a natural musical structure that composers have exploited in works ranging from orchestral tone poems to electronic ambient pieces. Contemporary artists working with light installations and digital media have found new ways to explore aurora themes, creating immersive environments that evoke the experience of standing under an active auroral display. These artistic interpretations often capture aspects of the aurora experience that scientific description struggles to convey. The emotional impact of witnessing something so beautiful and cosmic, the sense of connection to forces far beyond human scale. Literature inspired by the aurora ranges from scientific treatises to poetry to fiction that uses auroral imagery to explore themes of beauty, transcendence, and humanity's relationship with nature. Indigenous storytelling traditions from polar regions have been particularly rich sources of aurora-inspired narrative, offering perspectives on these phenomena that complement and sometimes challenge scientific understanding. The aurora continues to play important roles in contemporary environmental and climate discussions. As the Arctic region warms due to climate change, the conditions for aurora viewing are changing in complex ways. Warmer temperatures can lead to more cloud cover in some regions, reducing visibility for aurora watchers. Changes in atmospheric circulation patterns can affect how auroral particles interact with the upper atmosphere. At the same time, some research suggests that climate change might be affecting the upper atmospheric conditions where auroras occur. Changes in atmospheric composition and circulation at high altitudes could potentially influence auroral colors and intensities, though these effects are still being studied and are not yet well understood. The aurora also serves as a natural laboratory for studying atmospheric physics and chemistry under extreme conditions. The high-energy particles that create auroral displays can trigger chemical reactions in the upper atmosphere that wouldn't occur under normal conditions. These reactions can affect the concentration of various atmospheric gases, potentially influencing everything from ozone levels to the formation of unusual ice crystals. Some researchers are investigating whether auroral activity might affect cloud formation and precipitation patterns, creating indirect connections between space weather and terrestrial climate. While these effects are likely to be small compared to other climate drivers, they represent another way in which the aurora connects Earth systems to solar activity and cosmic processes. The study of auroral chemistry has also contributed to our understanding of atmospheric processes on other planets. When spacecraft observe auroras on Jupiter or Saturn, scientists can use knowledge gained from studying Earth's aurora to interpret the observations and understand what they reveal about those planets' atmospheric composition and dynamics. This comparative planetology approach has revealed that while the basic physics of auroral processes is similar throughout the solar system, the details can vary dramatically depending on planetary characteristics. Jupiter's aurora, for instance, is influenced not just by solar wind but also by particles from its volcanic moon Io, creating more complex and variable displays than anything seen on Earth. The aurora on Uranus and Neptune presents particularly interesting puzzles, as these planets have magnetic fields that are tilted at extreme angles relative to their rotation axes. This creates auroral displays that move across the planet's atmospheres in patterns completely unlike anything observed on Earth, challenging our understanding of how magnetic fields and auroral processes interact. As we continue to discover exoplanets, planets orbiting stars other than our Sun, researchers are beginning to speculate about what auroras might look like on worlds with very different characteristics from those in our solar system. A planet orbiting very close to its star might experience such intense stellar wind that its entire atmosphere glows with auroral light. A planet with an extremely strong magnetic field might channel stellar particles so efficiently that its auroras are visible from space as bright beacons. These speculations remind us that the auroras we see on Earth, beautiful as they are, represent just one example of a cosmic phenomenon that might manifest in countless different ways throughout the universe. Every aurora we witness here is both a local event specific to our planet's particular characteristics and a window into processes that might be occurring around countless other worlds. The future of aurora research holds exciting possibilities as new technologies and missions come online. Proposed spacecraft missions would provide even more detailed monitoring of solar activity and its effects on Earth's magnetosphere. Advanced computer modeling capabilities will allow researchers to simulate auroral processes with unprecedented detail and accuracy. New ground-based observatories equipped with increasingly sensitive instruments will be able to detect and study auroral phenomena that are currently too faint or subtle to observe reliably. High-speed cameras and spectrographs will reveal the rapid temporal evolution of auroral chemistry and physics on timescales of milliseconds or less. Perhaps most exciting are proposals for missions that would study auroral processes from multiple spacecraft simultaneously, providing three-dimensional views of how these phenomena develop and evolve. Such missions could finally answer some of the fundamental questions about aurora formation that have puzzled researchers for decades. But even as our scientific understanding of auroras continues to advance, the emotional and spiritual impact of these displays remains constant. People who witness their first aurora almost universally describe it as a transformative experience, something that changes their relationship with the natural world and their sense of connection to cosmic processes. This dual nature of the aurora maya as both a scientific phenomenon that we can measure and model, and as an aesthetic experience that touches something deep in human consciousness, makes it unique among natural phenomena. It bridges the gap between the analytical and the experiential, between the technological and the transcendent. In many ways, the aurora represents everything that is best about the scientific endeavor. It rewards careful observation, patient study, and collaborative research. It connects local observations to global patterns and cosmic processes. It demonstrates the value of combining advanced technology with human curiosity and persistence. And it reminds us that even the most rigorous scientific understanding cannot diminish the sense of wonder that draws us to study the natural world in the first place. The aurora also embodies the principle that the most beautiful natural phenomena often result from the most fundamental physical processes. The simple interaction between charged particles and magnetic fields, played out on a planetary scale, creates displays of such beauty and complexity that they have inspired human imagination for millennia. As you settle into sleep tonight, perhaps you can imagine yourself as one of those charged particles beginning its journey from the sun's surface. You would travel for days through the cold vacuum of space, part of an invisible river of matter flowing outward from our star. You would approach Earth and encounter its magnetic field, being gently guided along invisible pathways toward the polar regions. Finally, you would plunge into the thin upper atmosphere, colliding with molecules of oxygen or nitrogen and transferring your energy to them in a flash of colored light. For just a moment, you would contribute to one of nature's most beautiful displays, adding your tiny spark to curtains of light that stretch across hundreds of miles of sky. In this imaginary journey, you would experience the universe as the aurora does mine as a continuous connected system, where matter and energy flow seamlessly from stars to planets to atmospheres, creating beauty and wonder wherever the conditions are just right. You would understand, in a visceral way, that the boundaries we perceive between ourselves and the cosmos are largely artificial, that we are made of the same matter and subject to the same forces that create the dancing lights in polar skies. The aurora teaches us that beauty and science are not opposing forces but complementary aspects of a single magnificent reality. Every time someone looks up at dancing auroral curtains and feels a sense of awe or transcendence, they are responding to the same cosmic processes that physicists study in their laboratories and model in their computers. This unity of the beautiful and the understandable, the emotional and the rational, may be one of the aurora's greatest gifts to human consciousness. In a world that often seems divided between scientific and humanistic ways of knowing, the aurora demonstrates that these approaches can enhance rather than diminish each other. When you next have the opportunity to see an aurora, whether in person or through the photographs and videos that others share, take a moment to appreciate both its beauty and its meaning. Remember that you are seeing the visible signature of invisible forces that shape our planet and protect our biosphere. Remember that the light reaching your eyes has traveled an epic journey from the heart of our star to paint colors across our sky. And remember that in appreciating this display, you are participating in a fundamentally human activity, the search for beauty and meaning in the natural world around us. The aurora connects us not just to cosmic processes, but to countless generations of humans who have looked up at these same lights and found in them sources of wonder, inspiration, and peace. As the gentle dance of auroral light continues in polar skies around our planet, as charged particles continue their ancient journey from sun to earth, as our magnetic field continues its invisible work of protection and guidance, you can rest in the knowledge that these beautiful, cosmic processes will continue long into the future, creating displays of light and wonder for generations of Aurora watchers yet to come. Sweet dreams, and may your nights be filled with the gentle light of understanding and wonder, knowing that somewhere, always, the Aurora is dancing across Earth's skies, painting the darkness with colors born of starlight and magnetism, connecting us all to the vast, beautiful universe that surrounds and sustains us.